Hey, so in this video I'm going to cover the spatial filter on this, it running, and touch up a little bit on this axis, W axis, but primarily I'll be talking about the functionality of this stuff and running the laser and looking at the projection on a wall. Lady and gentlemen, I figure it's probably time to make another video as the YouTube algorithm is not going to be nice to me if I don't post something soon. So this is an update on the parts for the laser webcam surface flattening setup, and what we have here is this is going to be another appendage on my CNC machine. I'm going to call this one the W axis, and it's going to be holding the webcam sensor. This thing back here is evolution of the laser portion of the webcam and laser setup. And what I have here is a laser diode pulled out of that laser level. I'm going to still use the same one. And I have that on a 3D printed optical kinematic mount. So that thing fires through a spatial filter. And this spatial filter is comprised of two objective lenses. So there's one here and one there. And you can see how they can slide around and then get bolted down. And then in here is a flexure mount with a sort of a multiplier reduction of its motion. So this flexure here, by adjusting screw here and on the other side, this is going to move the flexure on the inside flexure grid by marginal amounts, and it's going to give me the same way of adjusting it that you would with like a compound adjuster screw without all the fine threads and stuff. And smack in the middle of there is a pinhole, and that's out of a piece of pop can, because aluminum pop cans are really thin and dimensionally pretty good. So tiny little hole, and I made that with a sharpened pin. You can see some previous videos on making pinholes and all that stuff. But that's epoxied in there. And then once the laser beam goes through the pinhole on the flexure here, it'll go through this final collimating lens, which is another microscope objective lens. I'm using 4x microscope lenses because that gives me a decent range of like distance, so I don't have to have everything extremely close. And because I'm making stuff out of 3D printed parts, you can't have everything squeezed all in together because it's just going to be a pain in the butt to try and design everything. After the laser beam's cleaned up through the spatial filter, it then goes through the Powell lens, which is right in there. And this is also on a 3D printed optical kinematic mount. The difference with this one is I have two stages of adjustment. So I have the core stage, which is here, and then you can see there's a spring here. And this spring is just a way of adjusting the angle, or this screw here is to adjust the angle of that spring. So this gives me a very fine adjustment of this one. And then this whole purpose is to then allow me to adjust very finely the angle of attack of this Powell lens to the laser beam. And then that way I can get rid of any curvatures that would be produced if they weren't perfectly aligned. And I kind of need that if I'm going to make a flat surface with this whole thing. The optical breadboard that this thing sits on is made of some tubular steel and then welded on a piece of bar stock. And then this has all been machined down, so it's all very nice and flat. It doesn't really matter anyway how extremely flat this is. I'm working with 3D printed mounts and stuff, so it's not like I need to have things on ball bearings and control the pivots and all that stuff. Like, I tighten these bolts down, all this 3D printed stuff is just going to squeeze and squish down anyway. So I have enough adjustability in things where I can, orient and adjust the beam and stuff. The collimating lens here, can't see, yeah, right there. This one has 2 rings of 3 pins, or 3 adjuster screws. This allows me to get 6 degrees of freedom, so I can control the angle of the laser beam coming out of the spatial filter, and also I can change its height and stuff. So if it's off to the left or whatever too much, then I can very lined up and parallel and everything with the Powell lens. And I can rotate it, and then I can also do some translations on it too, which is great to get it coming straight out here. For adjusting the power output on the laser diode, I'm just repurposing the electrical board I made previously. There's a lot of stuff in here that's not needed. There's a microcontroller and an ESC, and I was using that with the hard drive for adjusting the RPM of that, and ultimately that didn't really work out. So instead what I'm using is just this buck converter, and I'm just controlling the voltage coming out of here. I'm not even doing like a current control. I'm just controlling the voltage directly and then using that to the laser diode, and that seems to be working all right. On initial testing, this is probably the third iteration of this spatial filter. I find it does work, but it doesn't do everything I want to do. The beam coming out of this is not a perfect circle, and I want that. It is getting cleaned up though. It is coming out, and I'm getting a very nice Gaussian distribution of the shape of this beam, and it's going through the pinhole and everything. But the shape of this thing is kind of like a cat's eye, horizontal cat's eye, and I want it to be a perfect circle. So I've been playing around with the idea of using another hole to filter out the beam coming out. So I was messing around with just some more aluminum and stuff, trying to see if I could clean it up. Putting that right in front of the lens, that's going to produce a lot of distortions, which then the spatial filter cleans up, and that somewhat gives me the results I want. But I think for my first test of this complete system, I think I'm going to just omit this whole spatial filter and just run the beam directly from here to the Powell lens. And as long as I think I have the shape of this cat's eye horizontal and kind of even on both sides, I think the Powell lens here, which I don't even have mounted correctly, I think this thing will do a good job of spreading the rays of light coming off this thing uniformly, and I might not even have to deal with having the Powell lens at all, not a spatial filter. This thing does help with the interference lines, because I'll get those ones on the vertical above and below where I'm reading the sensor. I won't get them on the sides because I'm stretching the whole laser point out, but it does and will help with that. But the intensity of the light and stuff with the shape of it, I don't think it really matters. Let me know what you think. Also, if you know how I can clean this thing up perfectly to get a perfect circle out of this thing, because I'm not getting that with this setup, and I don't think it's because the pinhole is too big, because I made this thing extremely small. The pinhole is smaller than 100 microns. It's got to be probably 60 to 80 microns. The problem is I'm still getting the same shape. I'll get the same shape of this thing. Like everything goes through. It gets, the first objective is gonna focus that beam down to nothingness, going through the pinhole, and then it gets reprojected back out and collimated and straightened out with that one there. But as it gets scrunched down into nothing, it's still representing the shape, apparently. I thought initially it was going to clean all that stuff up. Yeah, I've tried changing the distance between where all these lenses are and the pinhole and adjusting that, but I find that if this pinhole is not exactly where it needs to be, I'll just get a ton of interference lines. And when you're messing around with this thing, there is definitely a point where you know it's correct and you know it's not correct in terms of the distance between all the lenses. After using this thing, I don't like this design anyway. This is a real pain in the ass to do. One thing I find is I'm needing to constantly take the objective lens for collimating off the entire system so I can project it onto a piece of paper and then see how the filtering is happening with the first lens and the pinhole. So that's a problem. What I've found is also that because of possibly the optics and stuff, if I do push this in and out, if I push it out too far or whatever, it does not, it won't collimate it properly, which is kind of a good thing if you're kind of checking it, because then you'll be left with a large spot. And if you project that thing, bounce it off of a mirror off the side of the room, and project it onto a wall, you can end up with like a 1 to 2 foot circle that represents the beam coming out of here, which allows you to adjust the first 2 stages of this thing and not so much worry about this, but also have it still in line with everything. And then when you're happy with it, then just bring this in and adjust it, and then collimate it back into a straight line. At some point, I'm probably going to come to the conclusion that I really should not be using this piece of crap, and then I should probably get a better laser diode that is more in lines with what I need. But this is what I got so far. But enough talking about this thing. This is the new W axis that I'm going to be putting on my machine, and this is a overkill size stepper motor, ball screw driven, and it's got 2 bearing carriages, 2 rails in there, and it all is pretty solid. So, and then I also have made this machine this adapter plate so I can get it onto my machine, and I'll place this so you can see how it looks. Oh, it's bloody heavy. So it's gonna go right in there, just like that. And it's what's kind of nice is it doesn't reduce the machine's travel at all. It doesn't get in the way of anything. As a refresher of what this thing actually does, it's just another axis, and it moves on the same direction as my z-axis, but it's independent of it. So it's going to be bolting onto the side here. There's a bunch of holes for some bolts that are going to go on the side here. And then I have a single one that's going to go onto the steel plate that also holds the ball screw nut. It's certainly not a very rigid setup at all, but like I'm not going to be machining anything with this. There's going to be, like, I'm going to be having sensors and stuff like that on this thing. So this thing really is not, the rigidity of this thing is really not that important. I did have a much smaller setup, and I had a few videos of it, and it was like a NEMA 11. This is a NEMA 23. But that NEMA 11 had some motor issues and stuff, and I had to go through a whole bunch of bullshit with Aliexpress supplier of it, and disputing it, and end up winning and decide to return it. And then I'm going to return the thing, and then I find out like they need all this other crap, like a shipping number and stuff. And a short story is like I kind of lost all my money on that thing. And if you're doing AliExpress stuff and you dispute something, my best advice is don't return stuff. Just go with the option of just keeping the thing and then having less money, because like that setup was going to cost me $60 to $70 for just shipping this crappy little NEMA 11 axes, which is, it was a tiny little thing. Like the shipping return cost was more cost than the actual thing, and I wasn't sure if the company was going to be reimbursing me or not. So yeah, that's what it is. The only good benefit is this thing is way overkill for its purpose. So I'm never going to have any issues with that stepper motor skipping steps on me, which is kind of important for what I'm doing. And it's ball screw driven instead of a lead screw. So the accuracy in the vertical axes would be a lot better. The device, which is going to be attached to this thing, will be the webcam sensor, and it's going to be on its own little kind of spring-loaded thing, which is kind of going to, it's going to move up and down and stuff. And it's going to be just touching the surface that I'm working on a single ball bearing, probably a large one, just to give me a nice kind of foot for this thing. But it's a single point. I'm not doing any like 3-point or any kind of that stuff, because I only want to be taking a measurement of a single point, which then the CNC machine will be working on. This whole laser assembly, what I'll probably do when I'm actually running the operation is have it attached to the table of the drill press, because this whole thing is sufficiently heavy and I don't think it's going to be moving around as much. Here's what it looks like with the laser running through the spatial filter. The lasers are going through the first objective lens, and then I have the pinhole with the flexure mount adjusted, so the laser will go through the tiny little pinhole, and then it gets collimated back out into a point, well, not a point there, but if it was properly adjusted, something like that, which is going to freak the camera out, it would be a point. when it's not aligned properly, just like this, where I have the collimating lens not in the correct position, it gives me the projection of what this will look like nice and large. So when I'm adjusting the spatial filter, I can see its alignment. Let me just bounce it off to the wall across the room. Yeah, this is about as ghetto garage optics as it gets. So what I've done here is on the drill press, and I'm bouncing it off a mirror there so I can project it back onto my garage door. Let me see if I can get out of the way. Alright, so it's bouncing off a mirror at a funny angle now, so it's not going to be a circle anymore. So as I adjust the collimating lens, I can focus this back to a point, but in this case I'll work with a large shape like this, and if I start adjusting the spatial filter, so this is the vertical axis, and then on the horizontal you can see what the interference effects are. The horizontal has a lot more wiggle room because the beam is not a circle. It's more like an oval shape. So somewhere there where it cleans up is good. And if I adjust the pinhole distance, so I'm moving it now away from the first objective lens, you can see what's going on there and the interference pattern. There it is back in the center, and if I go the other direction, you can see there the interference pattern. And if I adjust the pinhole location, I can move this around. When it's not focused correctly this way, I find it kind of a good way of kind of aligning where in the center of the laser beam the pinhole is, because you can kind of see sort of a better representation of everything. And then when you adjust it so it's nice and Gaussian like that, then you know you're in the center. So obviously, as you can see, that even though this is cleaning up relatively nice for what I can do in my garage, it's not a circle. So, and it's not like a nice little Gaussian kind of blob. So I'm thinking that I need to add another thing here. So I have like a little piece of pop can with a nice little clean circle, and I'll put this in front of the laser beam and we'll see what we get then. So this is the beam how we've seen it before, and if I slide this over, now we get this little circle, and then this thing can be then collimated down into a nice little point again. And let's look at this thing close up. So now here's the results I'm getting with the whole setup now, with the spatial filter, without the power lens, and now going through a pinhole. And looking closer, you can see the distortion. I don't know what you would call those things, halos, rings going around there. And then also there's some artifacts in like star shape patterns here going off in directions, and that's probably because the laser beam is bouncing around the spatial filter in ways that I didn't want to, I think. But yeah, that would cause problems as well. And putting this thing through a power lens the way it is, it will like stretch this side out, but it's going to leave like waves, like horizontal lines on the vertical. So that's no good. So if you know what I can do to improve all this stuff, that'd be great. But I think for now, I'm going to run this thing without the spatial filter and use the laser beam directly. At least I'm finding I'm getting better results. And in a dirty garage where there's tons of dust around, probably having a pinhole that can get easily clogged with crap in the air, multiple optics and stuff that can get dirty as well. It's probably not a good idea being around a CNC machine that's going to be possibly doing things like grinding for getting a flat surface. Here's an example of how much dust is in the air in my garage, and this is just because of me walking around kicking up dust on the ground. Here's sort of what it looks like with a Powell lens. Mind you, the Powell lens itself is very dirty now, so a lot of the artifacts you're seeing there is because of the dust on the lens. So definitely have to clean that up. But you can see how the point goes through and then it turns into a line. So I think I'll cut the video here because it's kind of getting long. And I hope you enjoyed this installment of Caveman playing with lasers. And definitely if you're looking for resources on lasers and stuff, there's better channels than mine. So yeah. What I'll be doing next is, as I said, I'm going to remove the spatial filter and just run the laser directly to the Powell lens. And I got to clean the Powell lens up. And I might even replace this laser with something a little better than that. But after that, it's on to completing the mechanics of the webcam sensor and getting the W axis onto the CNC machine and building the spring-loaded assembly for having that webcam touch the surface. And yeah, after that, there's a whole bunch of software I got to write to get the whole thing to run. And eventually, I'll probably come to the conclusion that using a CNC machine to create a flat surface with lasers is probably not a good idea. But until then, I don't know. So I will see you guys next time.